Thank you so much for having me, for the invitation. It's a great pleasure, and I'm sorry I couldn't make it in person to Stanford. Maybe next time. So today I'm going to tell you about the ZEF protocol, which is a protocol I worked on for low latency scalable private payments, and it's a joint work with former colleagues from Facebook, Alberto Stonino, Mahina Kelkar, and George Genesis. And I should say most of the work was done at Facebook last year when we were, most of us were there. Okay, so like I said, so I want to tell you more about anonymous payments at scale. So what do we mean by private or anonymous payments? I use the term interchangeably. What do we mean by anonymous payment? Well, first we mean a payment. So we want a sender to be able to send the money to one or several receivers, and we'd like a number of things to be true. First, the payment amounts and the resulting balances should be hidden. So I call that opacity. And we'd like the link between senders and receivers to be also hidden. So that so the idea is that if in the future a receiver actually uses their money, potentially publicly, to do something like or withdrawing the money, we'd like the origin of the money to be untraceable. So in comparison to a system like Bitcoin, we still want to we are going to actually use a system more like account-based. So we suppose that we're assuming that the users have accounts that are designated by addresses. So what I was going to say is we don't have people obviously use their real names. They use pseudonym and address. And in that respect, you would get the same thing in Bitcoin. But the difference in Bitcoin is you can reverse, sort of look at a public transaction and go back in time and try to figure out the pseudonyms or the addresses, who they belong to. And that's what we want to prevent here. Okay, and so I said I'm interested in anonymous payments at scale. So I mean the decentralized anonymous payments at scale. And so what do we mean by decentralized system, scalable decentralized systems these days? Yeah, and I should say, so in the past, anonymous payments have been also proposed, and it's been in the air since the 80s. But at the time, they more often than not, there was a trusted party to run the blockchain, to run the payment system. So nowadays, we're interested in blockchain decentralized systems where there's no trusted party. And what I'm interested in this talk is a scalable decentralized system. So scalability in decentralized systems. So that means like the ability to handle a large number of user requests has been definitely it's been definitely a popular topic, and there are many approaches to improve the scalability of blockchain. So one of them, for instance, in Solana, is simply to code the blockchain in a better way, like with the faster protocols, faster programming language. Other approaches include blockchain sharding or using layer 2s, such as ZK rollups, and that's sort of the roadmap for Ethereum 2.0. There are other approaches where you just create a smaller side chain and with a more limited number of validators, and then you are using a BFT protocol to run a consensus there, and it's going to be faster because there are few validators. So that would be a typical approach if you create a sidechain based on the Cosmos and Tendermint. So what I'm interested in discussing here in this talk is as a new approach based on a former work called FastPay, which you may also find in the Sui blockchain that was announced recently by former colleagues. And it's not based on a BFT consensus, more like based on what we call consistent broadcast, and I will explain that later. But what it buys us is that for the price of using a more limited number of validators, and assuming that validators can grow in size, we would like to have a form of linear scalability. So we would like to know that when we take larger validators, the throughput of the system also becomes larger, in fact, in the same proportion. And that's what's called linear scalability. And like I said, that was something we started with FastPay, which was a system for the basic payments, not anonymous payments. So that gives us a little bit of a roadmap here. We have on one side system for anonymous payments based on traditional blockchains, such as Zcash and Monero. And so they are anonymous, but the confirmation time is very high based on just the way the blockchain works, and the scalability is limited. On the other hand, we have FastPay, which is a very quick, which has very quick finality, is sort of infinitely scalable. Like I said, it's you just need to, if you want more throughput, if you want twice as much throughput, you just make every validator double in size, in number of machines. But FastPay didn't have anonymous payments. So the roadmap here is to try to take the best of both worlds and then provide a system that has anonymous payments and yet is linearly scalable and of course decentralized. Does it make sense? All right, I'm going to carry on. So, so the way we are going to do that is by introducing a notion of what's called in the paper opaque coins. And so we assume that we want a sender to be able to send those digital objects, which we call a coin, and whose value is opaque. So it contains some amount of money, but it's not going to be visible by the validators, at least. So that gives us a more detailed roadmap to build the ZEF protocol. And that's sort of what I'm going to follow in the rest of the talk. So first, I'm going to explain FastPay. Then I'm going to explain the extension with opaque coins. And then I'm going to explain, if I have time, another extension with removable accounts, which is, in fact, I think, a very important piece for the whole system to work, in particular, to bound the storage costs of the whole system. Yeah, and because if you cannot delete account, we'll see that having opaque coins actually at a high throughput forces you to increase the size of accounts over time. And if you can never remove them, that means the storage cost really can go to the roof, as basically as a function of the number of transactions you've done in the past. I should say, so the opaque coins, they are based on anonymous credential scheme called Coconut that was developed by co-author Alberto in 2019, and the full paper is an archive. Okay, so oh yeah, a few disclaimers. So I said, so we are going to introduce opaque coins. So a few things I should mention already. Users, they have an account that is designated by an address. For usability, sometimes you address, of course, you are going to publish it on your website so that people can send you money, and that's fine. You've revealed one address, but you should have other addresses that you keep secret, and we don't. So the protocol is not going to conceal when you use an address to send money. The protocol doesn't really conceal the activity of the address. It conceals how much you're moving and who you are sending the money, but it doesn't conceal the fact that you're using your address. So if you receive money on public addresses, the first thing you should do is move the money to a private address so that then people don't see when you actually use the money later on. Okay, and another disclaimer, we may also, in a practical realization of the protocol, there could be public fees that are not hidden. So people would see that you are paying public fees as a sender. And also we cannot really prevent senders from sort of disclosing who the receivers are after the fact. I mean, so that's something to So same thing, if you really don't trust the sender, the first thing you could do as a receiver is to move your money to a super secret account that the sender didn't know, and then nobody will be able to track your future activity from then on. Also, another disclaimer I should make, of course, is that when you interact with the protocol, I'm going to assume if you care about really protecting your identity, you're doing that over a private network such as Tor. Okay. So before describing, like I said, like the FastPay protocol and the opaque codes, and I wanted to give you a glimpse of the performance that we obtained in the system. So we prototyped everything, so first, how do we measure performance? So usually, what happens is you take a configuration and you pound it. You augment the throughput of the client transactions. And you observe the latency. And so normally what happens is while you are under the capacity of the system, the latency should be fairly flat. The servers are just responding immediately, and then after a while it's just too much, and then the system starts going slower, and because you are sort of over capacity. And so here we can see like. And so if you decide like in advance what is an acceptable latency, so you can go as you can decide what was the maximum throughput for that latency. Okay, and so now given that ways to measure latency in function of throughput, that way to measure the maximum throughput in function of a maximum tolerable latency. We can draw a curve, so and observe the effect of adding more shards to an authority, adding more machines to an authority, and so what makes us happy here is we can see that it's a linear curve. So that's validating what I was calling linear scalability early on. We want to know that when we are adding more machines, then it's a very predictable function. Like the observed maximum throughput is a predictable function. And a linear function of the number of shards. Okay, cool. And so here, so I could say that the throughput, so these measurements are made for the actual anonymous transactions. And we can see that the throughput is not super impressive as a result of using fairly complex cryptographic primitives and not attempting to also make the implementation any particularly good. And I will say a few words of that later. But the purpose of this work is to show the linear scalability, not necessarily to optimize the throughput for a particular configuration. Another thing that we designed the system for, and we are happy to see in the benchmark, is tolerance to fault. So, like I said, the system is designed so that you have a number of validators, and a client is going to interact with needs to interact with the quorum of them, and so we are already sort of including taking into account the possibility for some validators to be offline, and as long as the quorum of them is online, it doesn't really matter if some are offline. And in fact, we can see that adding faulty nodes doesn't. Is there a question?
I was curious what the latency is between the servers when you're measuring this.
The latency between the servers?
Like, are your servers spread throughout the world, or are they all like plugged into a 10 gig Ethernet switch that's local?
So I would imagine I would imagine they were like across regions, which is usually like 100 milliseconds or 200 milliseconds. Since we are doing anonymous payments, honestly, the latency is mostly the computation. But yeah, the details for the benchmarks are in the paper. Okay, so that was just a glimpse of the benchmarks. And to show you, I think that's also a way to clarify what we mean by linear scalability, so that it's in everybody's mind. And now I was going to give you an overview of the FastPay protocol, which is the protocol for just normal payments at the linear scale. Okay. And so once again, so the system is made of a number of validators, and we are assuming that at most a third of them typically is malicious. Of course, there would be weights and a ponderation in function of stakes in a practical setting, but here we are assuming everybody has the same voting rights. So the way the system works is designed for without making further assumption on the network. So we don't bound the delay of propagation of messages. So in that sense, the network is considered asynchronous. Of course, if the network doesn't relay the messages, then no progress is going to be made. But if we essentially progress as fast as the network allows us to make progress. So when a client talks to 2/3 validator approximately, we call that a quorum, and a quorum of votes, we call that a certificate, which is an important notion for the protocol, as we're going to see. So the communication model of Zeph is very interesting in the sense that validators do not talk between each other. So validators are those data centers that contain a certain number of shards, and clients talk to the validators in parallel, and then they hope to talk to a quorum of them and receive, like I said, a quorum of votes, which will be aggregated into a certificate. But the validators do not interact with each other. I mean, they could. There are some functionality of the protocol will be improved with a little bit of background communication between validators, but it really helps the analysis of the protocol when you consider they don't talk to each other, because in particular the analysis for linear scalability. Okay, and so also the execution model. So I said that the validators were sharded. So I mean, you can ask what are they sharded against? So we have a notion of account, and we assume that every account is owned by a single user. And so every account is going to be assigned a particular shard in each validator. For simplicity, I think in the paper, we assume that the shard assignment is the same for every validator, but the truth is there's no necessity for that. It could be a different shard assignment for every validator. And then what happens is like
is the shard assignment required to be public? So like if someone wanted to DDoS like one particular shard, could they like
for simplicity, we assume that in the papers, but it's not necessary. Actually,
you could totally hide the shards differently, and you don't know which data centers are sharding how, so it's hard to like target your DOS attack against one shard.
So in my company, we the design is going to be slightly different with the proper load balancer in front of the shards. That's for sure. I was going to say, so now, so we assume, so the execution model sort of assumes that we have a number of accounts that are owned by each owned by a user. And so now what happens is that if you have operations that concern several accounts, so typically a transfer has the account of the sender and the account of the receiver. So what's going to happen is we talk first. So it's going to be, obviously a transfer is activated by the sender. So the sender is talking to their account, and that's going to be where most of the work happens. But at some point, the transaction is really ready to be executed, which means we want to remove the money from the sender's account. We also want to add it to the receiver's account. And so the way it works is in terms of internally to a validator, the account of the sender is going to send a message across to the shard of the account of the receiver and say, hey, you have money. And so that message is internal to the validator. We call that a cross-shard request in the paper. And it's an asynchronous message that is internal and can take some time to arrive, can be very fast or take a little bit of time. And so it doesn't need to arrive at the same time in every validator, which causes interesting questions, and I will discuss that later. And so, right. So now, like visually speaking, so the FastPay protocol, if we sort of summarize everything I just said, so we have an account owner, and it's talking to a number of validators in parallel, like I said. And now, when you want to make a request, so it's kind of the simplest you can imagine. The account owner is simply broadcasting the request and say, hey, I want to make a transfer. Every validator is going to validate that request independently, saying, in particular, so for transfer, if there is enough balance. If the request is valid, you return a vote that says, okay, I can vouch this request is valid. And when you receive a quorum of votes, you aggregate and essentially concatenate the signature. That gives you what I call a certificate. And basically, at this point, the payment is final, it's confirmed. You just need to take that certificate and give it back to the validators, so that in step 5, so that the request is finally executed. But what you typically would do as a sender, you would also take the certificate and give it to a recipient to prove that you are sending the money. And the recipient can also confirm, take the certificate and send it to the validators, which would trigger execution if the execution hasn't happened yet. That's one way the recipient can trigger it. Okay, and so here the request here is typically a transfer from, let's say, from Alice. There's a sequence number because we want to be able to make several requests from the same account, and of course the order matters and the amount. Okay, like I said, so in an account, so you get a notion of address. So in FastPay, it's the owner's public key simply. Public number, a public balance, a sequence number, and then there's of course there are some metadata. So I'm going to maybe skip that one. So I mean, it's really just saying that just the details of what it means to validate and execute a protocol. Sorry, a request. So I was mentioning the cross-shadow requests. So something interesting that's happening in the system is that when the account of Alice wants to tell Bob, hey, you just received 3. That information is sent internally to each validator, and it doesn't need to really arrive at the same time. So in fact, actually, the example was the transfer from Alice. So Alice is removing 3 and sending it to Bob. And so what could happen is that a validator, and then Bob wants to take the 3 and send them to Charlie. Okay, and that's kind of the logical order that most validators are going to see. However, what could happen is that for a different validator that was maybe disconnected and reconnects, and maybe it's going to be the case that the transaction B1 happens before the messages coming from the shard of Alice arrives. And so you could see a temporary -3 in the account of Bob, and that's fine. You know, we're okay with that. It's only a fraction of the validators that could be in this weird state. And what matters is that at the end of the day, everybody has the same balance. Okay, and once again, that comes from so we have those cross-shadow requests whose order is not specified. But that's okay because the updates themselves consist in adding money, and adding money is a commutative operation. So at the end of the day, once everybody has the same updates, everybody has the same balance. So that's sort of the interesting part of FastPay. Okay, and I think I explained all of that. So the certificates, so the fact that they are signed by the quorum. Like by construction, you have you can only have one transaction that is certified for a given sequence number and a given account. It's like, that means that at the end of the day, all the validators, when they see the same certificates in every account in the same order, and so they are going to execute the same transaction, like I said, in the same order for senders and in arbitrary order for receivers. But we saw that commutativity shows that that it works, that it's going to converge. So at the end of the day, everybody has the same balance when all the certificates are consumed by the validators. Also, when something interesting is there's a notion of validation. To validate a transaction, a validator compares the amount to the balance and decides, okay, there's enough money on the account to send to validate that transaction. The balance is a function of what has been received yet. So it could be that, so like I said, the balance could have temporary differences, but that's fine. So like if worst case scenario, a validator is a little lagging, and so has a sort of conservative view of the balance and will not vote for a particular transfer. In that case, the sender, the client would simply need to wait. Basically say, okay, this wait, or perhaps send the missing information to the validator. So if a balance is lagging, so this validator hasn't received all the updates. So as a client, so maybe I can provide the missing certificate, and then I wait some more, and then I retry. Okay, and basically this is what I just discussed. The fact that you may, as a client, you may also have to update the validators if they are missing information. In general, the philosophy is the clients, they are the leaders of the account. Like if you are familiar with BFT protocols that are leader-based, so in this kind of system, the leader is the client and not a validator. Okay, so that was for FastPay, and thanks for getting there. And now I'm going to tell you about the opaque coins, which is the fun part where you use cryptographic primitives to achieve anonymity. So what kind of primitives do we need? So we need a notion of random commitment. So it's like forgive me if I'm explaining that at a relatively high level, by the way. So in the implementation, we use like proper like low-level implementation based on Coconut and bulletproofs, and the details are in the paper. So here I'm still staying at a relatively high level. So we have a random commitment, we have blind signatures. So blind signature is a primitive that allows somebody to sign a message without actually learning what they sign. Because the message has been previously blinded with a blinding factor that is noted U here. And now if you process the signature of a blinded message, you can apply an unblind operation and retrieve the signature of the original message M. I'm going to use also non-interactive zero knowledge proofs. So it's like magical object that proves that there exist secrets, such that a certain predicate is true on the secrets and maybe some public inputs. And optionally, we could use also special signature in the system, and that's certainly the case in the implementation. Okay, so we have a notion of FastPay account, and we would like to have opaque coins in the system. How can we do that? Well, one way to do that is basically we have a notion of address, which is the public key of the owner. What we could do is we could take a commitment on a certain value V and just bind that with the public key with the address of an account. So, and by binding, we have a notion of quorum and validators. Binding means essentially having a quorum of votes, so having a certificate on the pair, public key and commitment. So now the goal of a transaction is to create new coins that are bound to the receiver's public key and contains commit for the proper values that we wanted to send them, right? R is a blinding factor to hide the value. So now, if you are the owner of a coin, so first you need to process the certificate. So because it's not going to be stored on chain for you, you need to have it, and you need to remember V and R, and also because it's not visible there, right? Precisely by construction, we want to hide the value. So you need to remember the value inside your coin. And also, of course, the coin is tied to a particular account, so you need to control that account to be the proper owner of a coin. So now what does it look like to spend a coin? So and create new ones. Okay, so first, so you want to spend a coin, so you ask the recipients, hey, what are your accounts addresses? So the public key, PKJ, what are the values you want? So now you have yourself as a sender, you have an account, so and you control that account. So you're going to send a request that says, hey, in that account, I have a coin, I want to spend that coin. And we're going to do the same thing as before. We're going to validate the request and vote on it. And once you have a quorum of vote, you certificate that you intend to spend the coin. In fact, you kind of already have spent it. It's already marked as a spent at this point. Once you have a certificate that you have spent a coin, and this is the part that is sort of new, you would like to now create the new coins out of it. And this is what I call R star, and that you make a request there. And this is where we want to sort of magically create pieces of new coins that are blinded, so that you can aggregate them and magically unblind everything, aggregate, and create the new coins for the recipients. So that would be sort of the roadmap to create new coins. And so a new coin is this thing sigma j, that is like the certificate binding a public key and a new commitment value. So sigma j, so it contains a quorum of signatures. So every signatures by alpha is written here, sig alpha of Bj, and Bj is essentially a blinding of the pair PKJ CMJ. If you see, it's going to be anyway. I'm going to write it later on. So yeah, so the first thing compared to FastPay, I mentioned that we have coins attached to an account. We need to make sure that you cannot spend a coin twice. And so the most basic way to do that is simply by recording all the coins that have been spent in the account. Okay. So there's a spend list. And so now if you receive an operation that says, hey, I want to spend a coin. This is me, Alice, and I want to spend my coin sigma as part of the operation with sequence number 2. This operation obviously is valid only if the coin is correctly signed and what's in let's say the serial number of the coin, so the commitment is not in the spend list. And to execute that thing essentially says I'm adding CM to the spend list, and so it cannot be spent again. H here is an interesting thing. It's a commitment that says I'm spending a coin, but I'm spending it not to do anything. I'm spending it to do a precise operation that you don't know yet, and it's basically going to be a commitment on the content of the next request, which is the coin creation request, which I was writing R star. So like I said, so we want to, at the end of the day, we want those certificates for the receiver, PKJ and CMJ. So if we go back, what we would like is we'd like a quorum of validators to sign this thing so that we can unblind it and then aggregate. Okay. So now what's going to happen is a validator is not going to sign this thing for no reason. They're going to sign it if they have a proof that you actually spend a coin. So that's why in the creation proof, you give as input the certificate that you previously spent the coin, sigma. You give a description of what is it you want the validators to sign, so the blinded factor. And then there's a zero knowledge proof that explains that everything computes well, like you're not creating money. So that's what I wrote here. So you want a validator to sign all these expressions there, but of course you must verify under zero knowledge that the output values are the sum of the input value, everything is positive, and the blind signature is correctly, sorry, the blinding factor has been correctly applied. And once you do that, that's it. That's basically the whole protocol for opaque coins. And the interesting part, I think, here is that when you, I mean, one interesting part is that from the start, when you spend the coin, you need a commitment on what you want to do with it, and that's important. Otherwise, you could replay the certificate that spends a coin, the certificate C here. We don't want somebody to be able to replay that and achieve a different outcome. You can replay it for sure, but then you just create the same coins as the first time, so you're not creating anything. But that's because we were careful enough to add this hash in the original message that spends the coin. And that's so that's part of the analysis. So you for the proof, you can always define, so you can look at the sum of all the coins that are still spendable and tied to an account, and basically the proof goes by looking at that and showing that when we spend coins, we are not augmenting the total value of all the accounts. Okay, so that was for opaque coins. So for the sake of the presentation, I explained just spending one coin at a time, but you can actually spend several coins at the same time, as long as they are controlled by the same person. Because once you start spending a coin, you have a commitment on what the outcome you want that depends on all the input coins. So you'd better actually succeed in spending the other input coins. And then, of course, you can spend a coin and then get back the value of it publicly instead of creating new coins, that kind of thing. So it's all in the paper, but it's relatively straightforward from then on. Okay, so now the problem with the storage, the spend list, like I said, so it's needed to prevent replace. Like you have the certificate that some coin has some value and is attached to your account, but when the coin is spent, you obviously don't want it to be spent again to do something else. And so it requires having a list that grows indefinitely and is stored there in the account and can never go away. So the prime in FastPay, if you do that with the notion of account in FastPay based on the public key indexed by the public key of a user, the prime is that you can never remove an account. And the reason is because since the identifier, the address of an account is chosen by the users when they basically you give your FastPay, your public key to somebody, that somebody sends you money, and puff, that's going to create your account with the public key. And so that freedom is convenient, but also prevents prevents validator from cleaning up your account ever, because you could just recreate your account with sequence number 0 by just adding money to it later on, as you did the first time. So accounts can never, and if you recreate your account with a sequence number 0, then it means you can take the old certificates of transaction you produced before, and you replay them, and they're gonna replay against the sequence number 0, then 1, then 2, and you essentially minting money. So you can, and so that's the fact that you cannot remove accounts in FastPay. Maybe that's fine because each account is very small. But now, if you start adding a spend list in there, and we're talking on a spend list, it's something that you are going to check every time there's an attempt to spend a coin from the account. You're going to check the coin against the spend list. So it means the spend list cannot be put in cold storage. It needs to be really in the validator's memory. Long story short, we need to change a little bit, tweak a little bit more the protocol, And that's where I came up with the idea to add non-replayable addresses. So instead of using the public key of a user as an address for a FastPay account, we're going to use a unique identifier. Now, the problem is we are in a system that is supposed to be linearly scalable without a consensus protocol. So how do you generate unique identifiers? And the answer, and so, well, you could imagine, okay, we're going to use a common coin, and we're going to just, just toss coins and use that to create unique identifier. But that's going to be very, very expensive. And so the way it works is we are going to assume that there's already an account somewhere, and kindly ask them to generate a unique identifier for us. Every account has a sequence number. So if we take the unique identifier for the existing account and their sequence number, that itself is a unique identifier, and that's what we're going to use to create the new account. So in Zeph, and now I'm talking about Zeph, not FastPay. In Zeph, a unique an identifier, an address, an account address is a list of numbers, of sequence numbers. So it could be 1 to 135. And when you see 135, you know that this has been created by a parent account 13. And of course, you need some root accounts to start at the beginning of the system. So accounts that don't have a parent, and they need to be part of some Genesis configuration. Yeah, so that's how we solve the problem. And the beauty is that we can use the same schema as before. So creating a new account is basically just like a transfer from the owner of the existing account, that we can call a broker, to the new account holder that acts as a recipient. And so you have the same thing as before. You have a request, you validate it, you obtain a certificate, and then you can give the certificate to the recipient. And when you execute the certificate, that's actually installing the key, the public key of the recipient into the new account. Personally, I found it pretty cool that we were able to, so starting with just a payment system, we generalize the notion of account operation, and suddenly using a similar framework, we find that we can generate unique identifiers. I found that personally pretty cool and kind of unexpected. And unique identifiers, like I said, so now what's nice is that since creating an account is a one-time operation, creating an account for a particular identifier is a one-time operation that happened once and will never happen again. So if we delete the data, if an account is considered closed, so it's never going to be active anymore, we can delete the data of that account because we know nobody will ever be able to reopen an account with the same UID and replay the old certificates, which was the problem that I described before. And so there's a little bit of a race condition between account creation and transferring money into an account that doesn't exist yet. But that's fine. What happens is when you transfer money into an account, what you do is you add the money to the balance of the account. So you create, in a way, you create an empty account, an empty shell, so that you can track the money that you just added there. But you make sure that the account is not active yet. So there's no public key of a user yet. And so what I call account creation actually was more about account configuration. So creating an account means installing the public key of a user. So the operation adding money to an account and the operation installing the public key of a user, those operations, they do commute. So we solve our race condition in that way, if that makes sense. And that's what I was explaining.
If someone like create a whole bunch of transactions and send a tiny bit of money to to an account that looks like it doesn't exist yet, but actually will never exist, and then create like huge amounts of ledger
Yeah,
spam?
you can. Sorry. Okay, that was my. I've got a huge echo, so I was thinking somebody's speaking at the same time. That's funny. Okay. So you can totally send. The product doesn't prevent you from sending a micro dollar to a million accounts just to annoy people, but it's also kind of easy to prevent with fees. And yeah.
Is a fake account that is never going to be created. That will persist forever. It will never be garbage collected.
So if you send money to an account, a unique ID in the future, so yeah, you cannot remove that because you don't know, maybe that was intended. If you send money to an account that was already created and deleted, then you can delete it again. In fact, you can actually, you can run an algorithm that distinguish between UIDs that are in the past and those in the future. And when you try to recreate and send money to an account that is in the past and has been deleted, you don't need to recreate. You can decide immediately that you don't need to recreate it.
But I mean, I could send to a UID that's like 100 million entries long, for example, and that would just live in the ledger forever.
Right. Yeah. Okay. So you need a bound on the size of UIDs. So you need to agree, like maybe it's 10, maybe it's 20. Mm-hmm. So you can ask anybody to create an account number for you. Could be a validator. I mean, you don't need to have a 10 level of so yeah. So it's not a like bounding the number of indirection to 10, for instance, seems reasonable to me. And yeah, and so that was just a slide to explain what the protocol looks like at the very end. Like it's just we replace the public keys, so now we're tying a unique ID to a commitment number, but the rest is exactly the same. And that was it. That was it. I'm sorry, it seems like I may have taken a little bit more time, but so the conclusion is like I hope I conveyed the coolness of working with linear scalable protocols, DFT protocols. And I showed you that although the system was pioneered with just normal payments, now we have opaque payments and anonymous payments, I mean. And in fact, I also worked on other extensions like atomic swaps, and that's what I work on in my own startup.